Assalamu alaikum. We are going to discuss today solution of the non-homogeneous differential equation with the help of a new method, that's the variation of parameter. Earlier we discussed undetermined coefficients. There are two different methods completely. In undetermined coefficients, as we discussed before, we're having the function f of x. They make this equation homogeneous. We're having here, in general, we write here phi d, this is a differential operator, into y is equal to f of x. We'll put conditions on f of x, that f of x is a polynomial function, fx is an exponential function, and f is sine cosine function. I told you that if the function is polynomial function here, f of x is exponential function, any combination of these, we can apply the method we call undetermined coefficients. Undetermined coefficients. Now the question is, if this is not the case and f of x is a transcendental function, a transcendental function, we're having the exponential function, we're having here some, not the exponential function, we have the ln function, we're having the secant function, cotangent function, and so on, which are not coming in this function in f of x. So here we can't apply this method. We applied the new method, that's our variation of parameter, to solve the problem which is having the transcendental function. In addition to that, I would like to say that this method can be applied by any type of f of x. But because we are having the integration in that one and little longer in calculation, so we avoid it. And if this function is polynomial function, or the function is exponential function, or the function is sine cosine function, we prefer to use undetermined coefficient. And we can't apply undetermined coefficient, we go to the method, the variation of parameter. We're having here the equation a d2y by dx square plus b dy by dx plus cy is equal to f of x. This is my non-homogeneous form of my differential equation, second degree. I'm just taking an example. So here we want to solve this one, but here the function f of x is transcendental function. We can't apply the method here. Now what we do, again the same thing as repeated in this case. In this case what we did, we find here this function phi, the solution of this equation phi d equal to this second order differential equation. We get it c1 y1 plus c2 y2, and we say this is the this is the solution of the homogeneous part. Then we use this method and coefficient to find yp. We say it's particular integral, or sometimes people are saying it's particular solution. Both ways is correct. So there is notation in the book they're using as a particular integral or particular solution. I used to say particular solution. So then we write here our general solution of this one was y is equal to yc plus yp. So the first part is same. First part we also solve here, a d2y by dx square plus b dy by dx plus cy is equal to 0. I get a solution of this one, y is equal to c1 y1 plus c2 y2. Now here this method, the new method come, that's the variation of parameter. And we'll discuss the details of this one. We put here yp we want to find. Yp is equal to u1 y1 plus u2 y2. Here we have introduced two functions. That's u1 is function of x, u2 is also function. We introduced two functions, and we want to find these two functions so that we can have the general solution. This is my homogeneous part, yc. Then we can write yc is equal to y equal to general solution yc plus yp. So this is the method how we find it. Now obviously this is solution of this equation. If this solution of this equation must be satisfied, so we find here y dash of p. My y dash of p is equal to u1 y1 dash plus u1 dash y1, and the derivative of u2 and y2, as I told you, u2 is a function of x. So I get here u2 y2 dash plus u2 dash y2. We need here again the derivative, second derivative, We find a second derivative, y double dash of p is equal to u1 y1 double dash plus u1 dash y1 dash, then derivative of the second term is equal to u1 dash y1 dash plus u1 double dash y1. Then the third term that give me here u2 y2 double dash plus u2 dash y2 dash. Then the fourth term we get here u2 dash y2 dash plus u2 dash u2 double dash y2. Now I substitute the value of y1 y dy by dx d2 y by dx, and we compare the coefficients. When we compare the coefficients of this one, then I'm going to get here the equation. I'll get here the equation from there which compare the coefficients. We get here y1 u1 dash y2 u2 dash is equal to 0. And we get here y1 dash u1 dash plus y2 dash u2 dash is equal to f of x. So we get here two equations. Here u1 dash and u2 dash are unknowns. Here I skip the step that how we are going to compare the coefficients. You can find in any differential equation books the details for that one. So I get here these two equations, and with the help of these two equations I am going to solve it, and I am going to find the solution of this one that will give me u1 dash and u2 dash. And here I can just show you that how we are going to organize that one. So I just write here the equation, which is this equation to equation in the form of the matrix form. So I'm getting here this is equal to y1 y2 y1 dash y2 dash, and the unknowns are u1 dash u2 dash, and we're having here 0 f of x. I'm sure that you know the Cramer rule. We apply Cramer rules to find the values of u1 dash u2 dash. In Cramer rule we can have here u1 dash. To find it we need three w's. First w is the Wronskian, that's here determinant y1 y2 y1 dash y2 dash. Then having w1, replacing the first column by the unknowns 0 f of x. Then I have y2 dash. Then I have w2. My w2 is a determinant, that is here y1 dash, and replace the second column by 0 f of x. So these are my determinant, and then I can write here what's my u1 dash. My u1 dash is w1 over w, and my u2 dash is w2 over w. Now we are having here u1 dash u2 dash. We calculate the value. Now we want to find u1 and u2. What we do? We integrate it. We get u1. We integrate this one. We get u2, and we substitute the value of u1 u2 in this equation. We get here the value of u1. We get the value of u2. We find we're having this yp. So we can write here general solution. Our general solution, once we are able to find the value of yp, yc we have, then here y is equal to yc, the homogeneous part of the solution, yp, a particular integral, a particular solution, that give me the solution of my problem. Again, I just going to repeat. We're given here the differential equation. This is my differential equation, non-homogeneous. I want to use the variation of parameter method to solve it. To solve this one, I need here first the homogeneous part, as we did it before. Homogeneous differential equation, homogeneous part of the differential equation. We solve it. We'll get here this as a solution. Yc is equal to c1 y1 and c2 y2. We replace this one by yp by replacing c1 by u1 and c2 by u2. Want to find u1 and u2. To find u1 and u2, we substituted this equation yp in this one, and we then compare the coefficients. When we have this equation, we put equal to 0. That's why it's more simplified. We don't have y double dash terms here. So then we can have these two equations. These two equations for u1 and u2. We say it's a system of equation. We write in the matrix form. This is my matrix form. And then I use the Cramer rule to solve this one. With the Cramer rule, we're having here u1 dash is equal to w1 upon w and u2 dash is w2 upon w. We find here this is w and this must not be equal to 0 because we are going to divide this one. When this is 0, there is no solution. So then we find here w1. w1 is replacing by the first column by the constant, the right hand side. w2 is second column by the right hand side. And we find here the values of w, w1, w2. Substitute here. We get here u1 dash and u2 dash. We integrate it, we get here u1, u2. Here, instead of writing this determinant, we can write the value. What is the value of this one? This is 0, and multiplying here with the minus sign is minus y2 f of x. And this one here, we're having y1 f of x, and then we are having here the value of y1 dash f of x is equal to 0. So I can have here the new set of formulas for my u1 dash. So I can write here my u1 dash is minus y2 f of x over w, and my u2 dash is equal to y1 f of x over w. So we can just remember it that if we are having here u1, then I have minus y2, and when we have u2, we have y1. So here we integrate. So to find u1 and u2, we integrate it. What do we need? We need here y1, we need here y2, we are given f of x, we find w, where w is the Wronskian, y1, y2, y1 dash, y2 dash. When we are having these four things, then we are ready to find u1 dash and u2 dash. Once we get here u1 dash and u2 dash, we integrate this one and we will find the value of u1, u2. We substitute the values of u1 and u2 in this equation and we find our yp. So very interesting method, and we can solve this one. We apply this one also but for the differential equation of third order, but not more than that. So mostly we are having the equation of second order differential equations. So these details are there for you to apply it for the second order differential equation. So I give you the example to explain this one.